You know, there's a riddle that floats around engineering departments, usually mumbled by a frustrated CAD manager looking at a messy drawing. It goes, when is a line, not just a line?
Right.
It sounds like something you'd get in a fortune cookie, but if you're working in electrical design, specifically with AutoCAD Electrical, the answer to that question, well, it basically determines whether you're doing your job or just making pretty pictures.
It really is the fundamental question of the trade. Because if you open up standard AutoCAD and you draw a line, to the computer, it's just geometry. It has a length, an angle, maybe a color.
But it's dumb.
It's completely dumb. It doesn't know it's a wire, it doesn't know it's carrying 24 volts DC, and it certainly doesn't know it connects a power supply to a relay.
And that is the trap. We are diving deep today into the hidden intelligence inside AutoCAD Electrical, or AutoCAD as people call it. Our mission is to take you from just drafting drawing lines that look like wires to true electrical design automation, because those are two very, very different things.
Oh, they are. Automation means you are managing a massive interconnected database that just happens to look like a drawing.
And if you treat it like a drawing board,
You're just fighting the software every step of the way.
to help us navigate this, we have a pretty serious stack of sources today. We've pulled from a comprehensive analysis on systematic architectures, and we have transcripts from some great deep dive tutorials by Suntech Engineering.
Good ones.
We also dug into a candid forum discussion from CAD Tutor to see where real users are, hitting walls. So let's start with the lifeblood of the software, the wire. It seems simple enough. A wire connects point A to point B, but in AutoCAD, a wire is a very specific thing, isn't it? It's not just drawing a line from a power source to a light.
No, and this is where new users trip up immediately. I mean, technically, in the AutoCAD environment, a wire is still a line entity.
Okay, so it's aligned.
But, and this is a big differentiator, it has to reside on a specifically designated wire layer. That's the absolute key. When a line exists on one of these special layers, the software attaches what's called X data, or extended data, to it.
X data. That sounds a bit sci-fi. What is it actually doing in the background?
Think of it as an invisible backpack that the wire wears. That backpack contains all the links to the project database. It tells the system, hey, I have a wire, I have a potential, and I connect these two devices. Without that X data, it's just a line on a page.
So the software won't number it.
It won't number it, and it won't show up in your connectivity reports. It's a ghost.
Okay, this brings us to the first major piece of kryptonite we found in the systematic architecture source. I found this fascinating because I think every AutoCAD user has done this at least once to save time or, make something look smooth. Polylines.
Ah, the polyline trap. Yes,
Yeah.
This is a classic.
The source was incredibly blunt about this. It basically said AutoCAD Electrical is blind to polylines. Why is that such a big deal?
Because a polyline is a single object.
Mhm.
It can have multiple segments and vertices, but it's still one thing. AutoCAD's auditing tools are designed to look for simple individual line entities that represent a single conductor run.
So if I draw this beautiful continuous polyline that snakes through my schematic,
It might look clean to you,
Mm.
but the software's electrical audit tools see nothing, just empty space.
So if I run a from-to report on that drawing to send to the manufacturing floor.
You get zero connectivity, no wire numbers will generate. It's a complete ghost town.
Wow.
Because the software is looking for line entities with that specific X data on a wire layer. A polyline is a different object type entirely. If you have them, you have to explode them. Otherwise, they're just decorations.
That is a painful realization if you've just spent 3 days drafting a complex harness using polylines because they were easier to manipulate.
It is. You have to stop thinking about what's easiest to draw and start thinking about what the database can actually read.
Speaking of logic versus visuals, let's talk about how these wires connect. In the physical world, if I touch two copper wires together, they conduct. But in the digital world of AutoCAD, you don't actually have to be pixel perfect, do you?
No, and surprisingly, you shouldn't even try to be. This is where the concept of trap distance comes in.
Trap distance.
Yeah, think of it as an invisible force field around the connection points of all your components.
And what sort of range are we talking about here? Is it big?
It's tiny. The default is usually something like 0.025 units in imperial. It's a mathematical threshold. If the end of your wire lands within that tiny zone of a component's connection point, the software just says, yep, I see what you're trying to do,
Yeah.
and it snaps it into a perfect logical connection.
So it effectively allows for sloppy drafting.
I call it efficient drafting. You don't want to have to zoom in to 800% magnification just to make sure 2 pixels are touching. You just get it close, and the software handles the math. But you do have to be aware of that setting.
Why is that? What happens if I ignore it?
Well, if you're too sloppy, say you drop a wire 0.03 units away when the trap is 0.025, it might look connected when you're zoomed out, but the software says, nope, missed it.
So the data link is broken?
The data link is broken and your report will show an open circuit. And on the flip side, if you set your trap distance too large, you might accidentally snap to the wrong terminal if your component pins are really close together.
So it's a balance. Too small and you have to be a sniper, too big and you're connecting things that shouldn't touch.
Precisely.
Now, before we move off the wire itself, we have to talk about layers again. In standard drafting, I use layers for color, maybe line weight so it prints nicely. But here, the layer name itself is data.
Correct. It's critical. You map layer names to physical properties. So if I create a layer named, say, Arrayed 14 IWG, I'm not just making the line red. I'm telling the database that any entity on this layer is physically a 14-gauge red wire.
And that distinction pays off when we get to purchasing.
Oh, huge payoff. When you generate the bill of materials, the software calculates the total length of all lines on that red 14 IWG layer and tells purchasing you need 500 feet of red 14-gauge wire.
That is the difference between drawing a picture and building a system. If you just drew a red line on layer 0,
purchasing gets nothing. The panel builder gets a schematic that looks right, but when they go to the warehouse, the materials aren't there. And that's when the project delays start.
Okay, so we know what a wire is. But how does a symbol like a relay coil or a push button actually know that a wire is attached to it? This gets into what the sources call the secret language of the blocks.
Right, so if you were to explode a smart symbol in a can, which by the way, please don't ever do, it ruins them. But if you did, you'd see these invisible attributes floating around the geometry.
Okay.
The most important ones for connectivity are the X-term attributes.
X-term, like X files terminals. What's the question mark for?
It represents a direction. The X stands for connection, and the number tells the software which direction the wire is coming from. So X1 term connects to the right, X2 term connects to the top, X4 to the left, and X8 to the bottom.
Why does the software care about direction? Can't it just see a wire is nearby?
It helps with the auto routing and logic checks. If the software knows a terminal expects a wire from the right, and you try to bring one in from the left, it might try to loop it around awkwardly, or it might refuse to snap correctly. It's basically defining the landing pads for the wires.
So when you drag a wire near a symbol, the software is scanning specifically for those attributes.
Exactly. When it finds one within that trap distance we talked about, it snaps. If a symbol doesn't have those attributes, say you just drew a rectangle and call it a relay, it's just a dumb block. The wire will pass right through it like a ghost.
It's so interesting because visually, on paper, a rectangle is a relay. But to the database, without that X4 term attribute, it's just an obstacle.
It creates a gap in the logic.
Now, speaking of passing right through things, the Suntech engineering transcripts had a huge warning label on them. They were practically screaming, "Stop using standard AutoCAD commands."
Yes. This is the hardest habit for longtime AutoCAD users to break. You want to trim a wire, your muscle memory just hits the trim command. You want to move a relay, you type move VE.
And in AutoCAD, that's a disaster. Walk us through why.
Standard commands operate on geometry. They don't know anything about the logic, the database. So if you use the standard delete command on a wire, you might leave behind these little connection dots, the T nodes, just floating in space, because the software didn't get the message to clean them up.
And if you use standard trim,
you break the line visually, but the database might still think those components are linked. Or worse, you create a null reference. You're basically corrupting the integrity of your own circuit.
So the Suntech tutorial suggests using ATrim.
Yes, ATrim AutoCAD Electrical Trim. It's smart. It knows that if you trim a wire back, it also needs to clean up the connection dot that's no longer needed. It keeps the drawing and the database in sync.
And for moving things, there's this command called scoop. I have to say, it's a great name.
Scoot is essential. If you use standard move V on a component, the wires detach and they just stay behind. You've broken the circuit. But if you use scoot, it's like the wires are made of rubber bands. You move the component and all the connected wires stretch and move right along with it. The connection is never broken.
It's stretching the logic along with the geometry. That seems like a mandatory workflow change.
It is. If you aren't using scoot, you are literally redrawing half your work every time you make a small modification.
There was a bit of drama in that CAD Tutor forum source we looked at about connections. A user was incredibly confused about the difference between an intersection and a gap.
The classic crossing debate. This is where personal preference meets software rules.
The issue is when you have two wires crossing paths, they don't touch electrically. So some people want a loop, that little hump to show it's jumping over. Some just want a gap.
And the modern standard, like IEC and others, is increasingly just a solid line. It relies on the fact that if there's no dot at the intersection, they aren't connected.
This user in the forum couldn't get the loops to appear, even though they had the setting turned on.
This brings us back to the drawing properties. There is a setting called the Feature Scale Multiplier, or FSM. If your FSM is set incorrectly, the software tries to draw the loop, but the math says, hey, the radius of this loop is physically larger than the space available between these two wires.
Oh, it's a math failure.
It's a math failure.
Okay.
It tries to draw it, fails, and then defaults to just drawing a straight line. So the user thinks the feature is broken, but really their grid is just too tight for the loop size they've selected.
So if your loops aren't looping, check your feature scale multiplier.
Check the FSM and check your grid spacing. But honestly, that Systematic Architectures article makes a strong point that we should all just move toward the solid style. Loops clutter the drawing. The rule should be simple. If there's a dot, it's a connection. No dot, no connection.
Simple usually wins. Okay, let's shift gears to the advanced stuff. There is no actual cable object.
It sounds like a paradox, doesn't it?
Yeah.
We design cables. We report on cables. We have cable schedules. But the software doesn't have a single entity called cable.
So what are we looking at when we see a cable on a drawing?
You're looking at a collection of individual wires that are grouped together logically by a cable marker. That marker is the parent. It holds the data, the part number, the manufacturer. The wires themselves are just wires. They are children of that marker.
And this leads to that really specific error message people get. No conductors available.
Right, because the cable marker looks at the catalog database. It knows that part number CDL 101 is a 4-conductor cable. So if you try to associate a 5th wire to that marker, the software stops you cold. It says, hey, physically this cable only has 4 wires. You can't add a 5th.
That is a brilliant safety rail. It stops you from designing something that can't be built. The plug connection trick.
This is brilliant. It's for when you have a connector plugging directly into another component. Think of a module that plugs right into a backplane. Physically, they touch. There's no wire between them.
But a KD needs a wire to know they are connected.
Precisely. If they just touch, the database sees 2 separate objects sitting next to each other. It doesn't generate a from-to report because it assumes they're unconnected.
So what's the fix?
You draw a wire that is 0.0001 inches long.
1/1000th of an inch.
It is completely invisible to the human eye on a printed drawing. You will never ever see it. But to the database, it's a valid wire entity with X data. It connects pin 1 of the plug to pin 1 of the receptacle.
That is the secret sauce right there. But you have to be careful with layers, right? You don't want that tiny wire showing up in your wire list.
Correct. If you don't manage it, your bill of materials will list a bunch of 0.0001 inch jumper wires, which will confuse the heck out of your panel shop. And this is crucial. Set the wire numbering property for that layer to no.
So it doesn't get a wire number tag.
Exactly. It doesn't clutter your drawing. It doesn't clutter your BOM. It just silently bridges the logic so the database knows A connects to B.
A phantom wire for the sake of the database.
It's a perfect example of knowing how the software thinks, not just how it draws.
Another concept mentioned in the sources is fan in, fan out. This is for when you have a massive bundle of wires, like from a harness, and you don't want to draw 20 parallel lines across the sheet.
It cleans up drawing significantly. You fan the individual wires into a single source marker, run one thick line across the page, and then you fan out at the destination.
But there's a catch with that single line in the middle, isn't there?
Yes. That line is usually on a special layer called multi-wire. It's just a carrier. Think of it like a subway tunnel. The tunnel doesn't carry the people. The trains inside it do.
Right.
That line should never have wire numbers on it.
Yeah.
It's just a graphical placeholder. The actual logic jumps from the fan-in source directly to the fan-out destination.
So if you try to tag that thick line, you're breaking the logic.
You're essentially tagging the tunnel instead of the train.
Yeah.
It's meaningless data, and it breaks the association between the source and destination signals.
Okay, let's move to the payoff. We've talked about the how trap distances, X data, those tiny wires, but why do we go through all this trouble?
It's all for the reports. The drawing is pretty, but the manufacturing floor runs on the reports, specifically the from-to list.
The Suntech and Hagerman sources both emphasize this heavily. If you've done your job right, you can press a button and get a list that says wire 101 goes from relay 1, pin 4 to terminal block 2, pin 1.
And that brings us to wire numbering. In the manual days, you type these numbers in by hand. If you changed a page or added a relay, you erased them and typed them again. In AutoCAD, it's automated. But you have to understand the difference between normal numbers and fixed numbers.
What's the practical distinction?
Normal numbers are dynamic. If you insert a row into your ladder logic, all the wire numbers below it shift to accommodate the new line reference. Fixed numbers, which usually show up as purple text, mean hands out. Even if the drawing changes, that wire number will always stay 101.
Why would you want that? It sounds like it breaks the automation.
It's vital for retrofits or maintenance. If a machine is already built and labeled out in the field, you can't just change the wire numbers in the drawing because the software decided to resequence. You have to lock them down to match the physical reality in the cabinet.
The numbering format itself is powerful too. This concept of replaceable parameters. We saw things like %.
It's a simple code. % puts the sheet number in, % puts the sequential number in. So automatically, a wire on sheet 5, line reference 10, becomes wire 510. You don't have to think about it. If you move that circuit to sheet 6, the wire automatically renames itself to 610.
That saves. I mean, how much time does that actually save?
On a large project, days. And it completely eliminates the typo factor. Humans are terrible at sequential numbering. Computers are perfect at it.
Another huge automation piece is the terminal strip editor, or TSE.
The TSE is a game changer. In the old days, you'd draw your schematic, and then you'd have to manually draw the terminal block layout for the panel, hoping you didn't miss a wire.
And hoping you got the order right.
With TSE, the software reads your schematic. It sees every single wire that lands on a terminal symbol. It says, okay, I need a 10-block strip, and it generates the graphical footprint of that strip automatically. It puts the wire numbers on the left and right sides. If you did it right, it even shows the jumpers between terminals.
But the source warned that this isn't foolproof. If you didn't use the right footprint symbols, this all fails.
Yes. It relies entirely on the footprint lookup database. If your schematic symbol doesn't map to a physical part number that has a defined footprint, the automation just hits a wall. It might give you a generic box or nothing at all.
It all comes back to the database. We mentioned at the start that the drawing is just an interface. The real brain is that MDB file or .xls file running in the background.
That's right. Usually Microsoft Access or SQL. Every single time you click, you are writing a record to that database.
And standard AutoCAD users never worry about this, but AutoCAD users have this maintenance task called rebuilding the database.
It's like defragmenting your hard drive back in the 90s. Sometimes the drawing file and the database files just get out of sync. Maybe the software crashed, or maybe you used a standard UNDO command one too many times.
What happens then?
You might see a wire on the screen, but it doesn't show up in the report. Or maybe a wire number just refuses to update. Running a rebuild forces the software to rescan every entity on the drawing and update the database records to match. It's the first step in troubleshooting any weird error.
So have you tried turning it off and on again? Have you tried rebuilding the project database?
Pretty much. It solves about 90% of the ghost problems where the visual just doesn't match the data.
So to recap what we've learned today from this stack of sources, you are not drawing lines, you are defining electrical potential. Every click is a data entry point.
And the wire is the connector of that data. It has to be on a wire layer, it has to be a line segment, not a polyline, and it needs to snap to those X-term attributes on your symbols.
And please, for the love of clean data, stop using the standard move and trim commands. Use scoot and 8trim. Your future self will thank you when the reports generate correctly.
Absolutely. The discipline you put into the drawing stage pays massive dividends at the reporting stage.
The Systematic Architectures article ended with a look at the future, things like AI and smart blocks in the 2024 and 2025 releases.
It's fascinating. Software is starting to predict where you want to place components based on how you've done it before. It's moving from just automation to actual suggestion.
Which leads me to a provocative question to leave our listeners with today. If the drawing is really just a visual interface for a database, at what point does the drawing become secondary? Could we eventually reach a point where we design entirely in the database, defining connections in a spreadsheet, for example, and just let the software generate the drawing for us?
That is the holy grail of generative design. We're already seeing glimpses of it now. If the logic is perfect in the data, the visual representation is just. It's a view. Maybe one day we won't draw wires at all. We'll just define the from and to, and the AI will route it perfectly for us.
A world without wire crossing loops. I don't know if the forums are ready for that.
I don't think they are, but the technology is certainly pushing us there.
Until then, check your trap distance. Stop using the spacebar to repeat the line command when you should be using the wire command, and keep your data clean.
And rebuild your database.
Thanks for listening to The Deep Dive. We'll catch you on the next one.
Thank you for watching the full video. Don't forget to subscribe to the channel and ask your queries in the comments below.